Good afternoon all. Welcome you all for the second session of one-day international seminar on advancement in concrete technology organized by Department of Civil Engineering in association with ICA Student Chapter, Telangana. I request Dr. Pallavi Badri Ma'am, Head of the Department Civil Engineering VJIT, to have a keynote.
Thank you, Shrija. I would like to welcome all. It's a welcome address. Fine. Respected Director Sir could not join this because of his urgent appointment. So, respected Director, Professor E. Sai Baba Reddy Sir, Institute Principal Dr. A. Padmaja, today's Honorable Resource Person Dr. Shane In Chen, Professor University of North Carolina, participants from the several universities of from India as well as from the other part of the globe. My dear colleagues, very good evening to all and welcoming you all in the second session of the today's one-day seminar, international webinar on advances in concrete technology. I'm pleased to share you all that 800 participants we received for this international webinar, and it's really glad for us to as all participants are believing us and they are joining with us for the event. Today's topic by Professor Shane is self-sensing and magnetic concrete for power transfer. Certainly will enlighten our participants and it will be beneficial to all of us in taking this research ahead in this area. So with this, I would like to welcome you all again for the second session for this say one day international seminar. And I would like to hand over session to Ms. Shrija. Thank you, Shrija. You can take over the event.
Thank you, ma'am. I request all the participants to mute your mic. I'm grateful to introduce today's session speaker, Dr. Shen Chen, Professor Civil and Environmental Engineering, University of North Carolina, Charlotte, USA. And he was going to deliver a topic on self-sensing and magnetic concrete for wireless power transfer. Dr. Shen Chen, prior to UNC Charlotte, he taught at the University of Alabama at Birmingham. His research focuses on non-destructive health monitoring of power transmission and bridge systems using remote sensing techniques, such as 3D terrestrial LiDAR, laser vibrometry scanners, and small format aerial photography. His other energy-related research include carbon capture and storage, ceramic candle filter testing for emission gas filtration during coal-fired testing, and more recently, study of power system resilience during extreme climate events. He is a member of the Forensic Engineering Division of the American Society of Civil Engineering and has the lead the US team to investigate the aftermath of Super Typhoon Haiyan in the Philippines and recently in Puerto Rico for Hurricane Maria. He has 90 peer-reviewed journal publications and gratitude 8 PhD students at UNC Charlotte. So we welcome you to the session and I'm handovering to you. Thank you for joining with us.
Okay. Thank you, everyone. And I appreciate very much during this pandemic that you are still, everyone is acting safe and also ensuring that we are still active in research and advancements of technology. So thank you all the participants. And I want to thank Dr. Suhasan for organizing this. And thank you, Dr. Pavavari, for the welcome. The work that I'm going to present is ongoing research at UNC Charlotte. And I wanted to give you a inspiration of what we are doing. Okay, so this is the outline of our presentation. As you can see that I'm actually introducing multiple concepts, but all of them are based upon the quality of a modified concrete material. Okay, so that is the inspiration of today's presentation, and we we get a lot of issues regarding concrete, especially for aging concrete materials. As Srija has mentioned, my background is in inspection science. So anything that can be used to detect the changes in concrete material is of interest to me. And one of the issues that we have seen over the years is the aging infrastructures are slowly demonstrating our understanding or the lack of understanding of concrete material in general. And so these are some pictures of what we have taken during the decommissioning of a nuclear power plant in the US. And we noticed that one of the significant problem is the encasing concrete materials has significantly damaged through the process, through the years. And so what can we do to improve on the concrete material? And one of the challenge of nuclear concrete is that the material are massive. Okay, so mass concrete is an issue for any inspection technique. So this is the history of the nuclear power plants used in the US, and are you able to see my screen still?
Yes, sir, we can able to see your screen, sir. No issues.
Okay, okay.
Sir, can you please enlarge it as it was in a window?
Enlarge. Okay.
Yes, sir.
Yeah. Can you see now? Are you able to see my screen?
Yes, sir. Yes, sir.
Yes.
Okay, thank you. And I'll try to speak slower because of the challenges in technology. So as you can see, most of our nuclear power plants in the US are close to 50 years of their utility life. And many of them are designed 50 years of their life. And this is one of the challenge. While there are new plants are being designed, but the old plants has been recommissioned, extended their service life. So how can we handle those concrete material has always been a challenging topic. Again, these are pictures that we have taken on those corroded concrete encasing the nuclear and other concrete structures. Okay, so we trying to simulate one of the challenge of nuclear concrete is that they are heavily reinforced and pre-stressed. Okay, so with all this massive amount of materials, you can imagine it's really hard to use any kind of non-destructive testing technique. So we model. Oh, yes.
Sorry for disturbing you. So many participants are saying that your screen was not visible.
Okay.
Can you please resume and open it again?
Yes, I will. I will do that. Yeah.
Thank you, sir.
Okay. Can everyone see my screen now?
Yes, sir. Yes.
Okay.
Right.
So to demonstrate the challenge in nuclear concrete material technology, we model a beam with heavy reinforcement and the pre-stressed tendon. And as you can see, as high temperature are propagating through the material, which is what we expected from nuclear concrete, we recognize that the temperature that you can measure from the far end of the material are actually not significant. Okay, so this is a case of undamaged concrete versus a damaged concrete. And when heat propagates through this material, we see that there is a challenge in being able to measure the temperature change using existing technology. So these are many different non-destructive testing methods that um, could potentially try, but none of them will be able uh, to see the change in the concrete material. I think I'm gonna reshare my screen again.
So sorry for 2 minutes. Participants, please don't share your screens. Only speaker have to share the screen. You can continue, sir. Thank you.
Okay, yeah. And so as seen here, those are existing NDT methods. They are very good for buildings and bridges, but are definitely not sufficient for foundation type or nuclear concrete structures. Okay, so we asked ourselves a question in our lab. Is there anything that we could do to enhance the sensing of concrete material? And so we come up with this idea. Actually, we didn't come up with this idea, but there are, since the early 90s, there are a few group of people who are investigating the possibility of developing self-sensing concrete material. And so we look at what are the possibility of making concrete self-sensing. One of the technique would be to use embedded or topical sensors, which may be adding fiber optic sensors within the concrete material, adding other kinds of sensing embedded sensors, such as piezoresistive fibers, carbon nanotube coatings, and so forth. But each of this technique has its own challenges. So the technique that we come up with is to enhance the material property of concrete material by adding conductive elements. Okay, I'll just leave it as that because there are many conductive elements that we can add into concrete material. Okay, and concrete itself has very poor, actually poor conductivity. Okay, so not resistivity. And so typical concrete, reinforced concrete, you already have rebars, which has high conductivity. But as you can see, one of the challenge, and then I'll point out more through the presentation that there are actually many aspects to electricity concept as we are trying to develop this technology. But the key is if we can add certain conductive elements into concrete and make it more electric conductive, then we will be able to make concrete self-sense. Okay, so by self-sensing, we meant that we are adding an electric current to the conductive element. And then by measuring the change in resistivity of the material, we were able to project the change in the condition of the structure. So some of the studies that we are trying to develop are if the self-sensing concrete can feel stress or strain. And one of the challenges is to derive the correlation between electric properties and the physical stress strain properties of concrete. And so this is a very condensed version of our derivation. And ultimately, we wanted to be able to present the strain change in a concrete material as a function of the change in resistivity. Okay, and here is another challenge. So we don't really measure resistivity. Most of the time, we're actually measuring the change in voltage because you have an input current, which is in voltage. And then what we're really measuring is the change of the current of the material. And another misnomer in the development of this technology is really that it is hard to define resistivity for typical concrete structural elements because of the changing geometries and so forth. So most of the time, what we are really doing is measure the change in voltage, okay, which can be translated into resistance of electricity in the material. Okay, so using Ohm's law, here's another very important point, and I'll point out later that there is actually in the equation of Ohm's law, there's a voltage, there's current, and there's resistivity. And the relationship when you introduce a current into concrete, you actually not only change the voltage, but also change the current. Okay, so resistance is a function of both the amount of current you introduce into concrete, as well as the pressure drop, because voltage is really um, the change in the electric current pressure going down your conducting element. And there are many things that would actually impact on your concrete resistivity. Okay, one is the volumetric fraction of the amount of conductive elements that you add into the concrete. Another thing is the presence of ions, because we know that regardless of the age of the concrete, there is always a little bit of water, pore water within the concrete material. And that has allowed some free ions migrating within the concrete material. And so those free ions can impact on your electricity current and the composition of the pore space. So pore space, the size and the volume is also another critical element. And then finally, the aggregate location within your material itself is a critical element. Okay, and I will describe a little more. I have a schematic later to show what we visualize was within this material. Okay, from the measurement perspective, we could use direct current or AC current, alternating current. And the different techniques actually has significant implication in concrete element, because a typical concrete element with its massive volume, it represents more like a capacitor. So if you use a direct current projecting into the concrete material, the concrete would actually absorb those electricity. So if you look online, there are people actually studying how to use concrete as a storage, energy storage technique for electricity. Okay, so that shows you there is a challenge in selecting the current technique. So we choose to use AC current, a single frequency current, or the three-phase that we use typically at home. But either one of them, you have to select a specific bandwidth so that you can you can avoid the problem of leaky electric current. And so since we use AC current, so the voltage that we measure is actually a cyclic function. Okay, and I will show you in a minute. So the material, the conductive material that we choose is actually recycled steel residuals. And I apologize for the misspelling there, but the residual material is a waste material during the steel forming process. So this is the stuff that typically the steel fabricators would send it to steel mills to be remelt to make new steel, or they're just dumped in the landfill. Okay, so this particular material becomes an extremely low cost and sustainable material, because we are not leaving it in the elements. We actually are reuse this material, so it becomes a very valuable stuff. But the processing of this steel material requires both sieving, because as you can imagine, it involves different shaving size and so forth, and a lot of dust as well. So it needs to be cleaned because it may be greasy. It needs to be processed in order to use into the back into concrete. And in our laboratory, we try to use different proportions of this material adding into concrete. And I will not go too much into the proportioning, because we're really, the idea here is to introduce the technology. Okay, and another thing in the design of this self-sensing concrete would be, how do you embed the sensing element into your material. So this is what we have built for the standard concrete specimen, wherein we put copper wires and leaving about 25 millimeters of opening, so that when electric currents are introduced through any of these conductors, the rest of them will become sensing elements. Okay, so in this particular case, we could either introduce the current from the top wire or the bottom wire, and then all the wires within would be the sensing elements. And this is the visualization of what's happening, just to demonstrate the complexity of the electric current going through the system. Okay, so you have our typical solid aggregates, both large aggregate and small aggregates. You have the cement matrix, and then you have both dust-like conductive material, which are steel dust, carbon steel, and then there are also air voids and fiber-like material. So because of the steel fiber, your end product is actually stronger than typical concrete, okay? But because of the added complexity, so it's really hard to imagine the path of the electric current going through the material. So one of the challenge in this study is really, we haven't been able to establish the theoretical model of what's happening within the system. So the correlations that we have developed are all based on experimental correlations. We first start testing on standard concrete cylinders. So in order to measure the self-sensing component, we have to drill holes and then embed those copper wires to do the self-sensing. Okay, and then we do the standard compression test on those specimens. And as you can see, the resistance change is actually consistent with the compression load with some variation. And this variation is all material property dependent. And this is the, previously that was the 7-day concrete. And then for the 28 days concrete, we actually were able to distinguish 3 different phases of the transition. And then we make a correlation. So you can imagine during the small strain loading, because of the loading setting, okay, you are expecting to have a larger deviation of your measurements. But then as you load to a higher strain rate, higher strain level, you will get a more consistent measurement. So this gives us a lot of confidence in the self-sensing capability of this concrete material. And then we start developing concrete shot columns. And this is, again, the standard setup of using those conducting elements, the sensing wires. So the self-sensing component consists of 2 parts. One is the fibers that we add into the materials, and the second is the sensor actually itself. So this, which are those copper wires built into the material. And we did Excel testing, and this is our test setup. So this is voltage readers. We measure the voltage change throughout the system, and with the current introduced into one of the ends. And this is the measurement. So as I mentioned, because we are using AC current, so you can see the single phase response. So when you, in this case, you will use the average values of the voltage change as your reading. And this is the outcomes from a 2% column. And we do cyclic loading so that we can ensure that our readings are consistent and repeatable. So you can see that we load this beam in a cyclic manner for 3 cycles. Well, loading, unloading, and then loading, unloading again. And so for the 3 cycles, you can see the change in strain, which is read by attached strain gauge, and then by the resistance or the voltage measurements. Okay, and to make a practical application, so you have to use the readings that you developed through the technology. And what you were able to accomplish is that you see that there is a assumed linear correlation, so that by matching the linear correlation with the theoretical equation that we have derived. So here there is a empirical factor F that you have to embed into the measurements, so that you're able to correlate the change in resistance to the change in strain. And then at that juncture, we know that the self-sensing is a very useful technique, and we are actually developing good correlations between stress strain and also the voltage change in a self-sensing concrete. And then we have another student who got interested in studying the thermal cycles of the concrete material. And so we do what we call the cool down test. We first take the specimen and then put it in the oven and heat it up to 100 degrees Celsius. And then we allow it to cool down. And then we trying to correlate the thermal properties, which is the temperature change versus the resistance change in the concrete material. Again, the same technique, we use applied currents through the material and then measure the change in voltage. And at this juncture, we also realize that there is actually another component to it, which is the current is also changing through the material. And so in this particular test, we also did both the voltage and the current measurement change. This is a finite element simulation. So to understand what physically is happening to those free cool down elements, we developed this finite element model to show the temperature change through the cooling process. And as you can see, the finite element models is consistent with what we measure using a thermal infrared camera. Okay, so this infrared camera is measuring the surface change of this element, but the finite element results that we're showing is actually the inside of the element. But the general idea is that the surface of the material is cooling at room temperature. And so you have a hot core, and then you have a cooling surface surrounding the hot core material. And this red spot here is actually where we have the strain gauge and all the epoxy. So that has a different cooling effect to the element. So we understand that what we're measuring is accurate. And then using temperature change versus the current change and the voltage change, you notice that there's actually a drop in both voltage and current measurements. Okay, so this shows you when you have a 0%, when you have no steel fibers, you actually see an upward trend. But when you add the steel fibers, you see a downward trend. Okay, and 2% material performs better than the 1% with the filler materials. Okay, so it becomes apparent to us that the technique needs to have both current and voltage measurements in order to accurately quantify the change in resistance. But that makes the technique a little too complicated. And so again, we're trying to develop a correlation between temperature change and the voltage measurements. And we were able to use both Joule's law and the temperature change to develop a correlation between the two. One of the application of thermal concrete is the new idea of using concrete as a energy storage technique. So there are two applications. One is to apply this as a fossil or any kind of mass energy production plant. So during fossil energy production, we use a lot of water because the water would be heated up to steam, and the steam pushes the turbine so that we can generate electricity. But then usually at a fossil plant, we will release the steam into atmosphere. So with this concrete energy storage concept, you can actually circulate the the steam through those concrete pipes. Okay, so it's shown in this picture. So this is an actual thermal energy storage plant in Germany that they have a lot of those concrete cylinders, and they allow water to pass through them so that through heating up those concrete elements that you are storing heat. And then when the demand of energy is going down, you can recirculate cooling water through those concrete pipes so that you can regenerate electricity by removing the heat from those processes. And so that is one significant application of this new technology. The other application of this is actually used for buildings. So using building concrete as a temperature regulator and as well as a energy storage and reuse is becoming a very attractive concept. And so in our laboratory, we also trying to develop such a technology, but at the same time, we try to introduce the self-sensing into these elements. The reason we do that is because, as you can imagine, going back to this slide, if any of these elements are fractured or damaged, because they are so massive, you will not be able to detect the change within the storage system. And so if we can make this element self-sensing, then we will be able to pinpoint which cylinder was damaged. And then we can replace that particular cylinder. And so it becomes a very effective technique and reduce a lot of labor and also cost to the concrete storage technique. And so there is advantage of doing such a technology. And to develop such an element, we use thermal quantification of how much energy is stored into those cylinders, and then we embed using the fiber reinforced concrete as well as the embed electrodes into these elements. Okay, so this is our energy storage concrete design. You have a heat drum where you circulate heated water through the system, and then the water pipes, we introduce the hot water through those elements. And we have two different versions. One, we have four pipe cylinders, and then the other one, we have a single pipe cylinder system. And this is where, and again, we are introducing some ongoing research. So I wanted to point out some of the challenges that we encounter doing this research. Okay, so this is our single pipe concrete element. Okay, so you can see we have embedded a lot of thermocouples, which are it's not visible because they are the K-type thermocouples. And then those green wires are our couple wires for the voltage change measurements. Oh yeah, this red coils are the thermocouple measurements. Okay, and so this is the experimental setup. We have the heat drum that heats up water that circulates through this pipe, and that would increase the temperature. Again, we use finite element simulations to show, and also use infrared to show exactly what's happening with this concrete elements. So we were able to heat the elements up to 100 degrees Celsius. And then during the heating process and the cooling process, we do the correlation between the voltage change. So here is the temperature change versus finite elements that we did on those concrete cylinders that we made for the energy storage. This the results are within room temperature, so there is no insulation elements to this particular experiment. Okay, and this is the another thing that we found. So when the heat pump was on and off, it actually the electric interference, the EMF interference to our experiment is visible in our measurements. So that's one of the limitations of this technique, is that because you're measuring the voltage change, so any of the large power systems surrounding your measurement technique need to be avoided because they would interfere with your voltage measurement. And which can be avoided by shielding, but we currently are still learning how to shield those kind of EMF effects. And this is the voltage change measure at different locations along the cylinder. So this another demonstration important to point out here is, as you can see, the result can have big variations. So the length of your measurement, the distance effect is critical. And so we recognize that actually, if you have a longer measurement range, you actually get better results, as shown here. 76.2 centimeter give us the best correlation. The row 1, row 2, row 3 are just at different positions along the cylinder. And again, to make practical applications, you need to be able to correlate empirically the voltage change and the temperature change. So here it shows that we are trying to use a linear function, actually a log function to correlate the voltage change and the temperature change. Okay, so that is the self-sensing part of the presentation. Next, I wanted to discuss about the magnetic concrete component. And the inspiration for this is actually in the wireless power transfer. So in our laboratory, we also do a lot of railroad propulsion technology development. Why do we do that? Because our interest is still in the civil aspects of this. And so this is research work that we collaborate with both electrical and mechanical department. And the challenge here is there are ongoing research on how do you wirelessly charge electric vehicles. And so instead of a train here, if you imagine a car that is powered by lithium-ion batteries, so those batteries need to be charged. Right now, when we use direct wired charging, there is a limit on how fast you can charge those cars. So if we could have a lot of wireless pads underneath a car, then you can potentially charge cars while the car is still moving. So that is the inspiration behind this particular research. So the question is, how do we design that? And in our laboratory, because we focus on railroad technology, so we wanted to develop similar charging technology for electric locomotives. And concrete has very poor magnetic permeability. Okay, so in order to make concrete materials magnetic, we have to modify the concrete material. So luckily, the carbon steel fibers that we have used for our electric current research has a relatively high permeability, which is about 1,000. Not the highest materials, but again, there is a trade-off between cost and also the material property here. Okay, so just refresh your high school magnetism and then also to introduce what is inductive power transfer. So there are many methods to do wireless power transfer, but the most accepted technique, because we are interested in high speed and also high power power transfer. So the most common technique accepted is the inductive power transfer. So inductive power transfer requires two coil systems. One is the receiver coil that will generate electricity into your locomotive, and then the transmitter coil, which is where you use current to generate an electromagnetic field. So this electromagnetic field would result in an induced magnetic field on the receiver end. And then use power electronics, you can convert that electromagnetic into electricity. So this is the general idea of wireless power transfer using induction. And this is a really neat idea because it combines both Ampere and Faraday's principles into the technology itself. Okay, but a critical challenge in the design of such a technology is actually in that when you introduce the current into your system, you actually need to make it into a single or multiple bandwidth magnetic field. In other words, again, we get into the argument of DC current or AC current. Okay, and so in order to make this efficient, you actually have to take DC current and revert that into a single frequency or a bandwidth of frequencies to optimize the transfer of the magnetic field in your system. Okay, so there are a lot of theories that are out there that talks about the advantage of an optimal frequency. And one of the things that you wanted to do is to avoid the resonant frequency of the system. Okay, so for any coil system, because of the size of the coil and the number of turns, you actually have an optimal frequency that is not or very close to the resonant frequency, but avoiding the resonant frequency of the system. So by being able to transfer select the design of your coils and then determine what is the optimal frequency for the magnetic field power passing is a critical part of the research. Okay, and here is where the practical application demonstrates. So we will imagine to have a pickup coil, which is the receiver coil, embedded underneath the vehicle, and then the other wire coil will be embedded.
अरे वो पीएम मोदी के साथ भी है.
Oh, was somebody talking? So there is a receiver coil that is embedded into the pavement of the vehicle, if you will. Okay, and so a typical coil wire is what we use the ferrite lead wire. So ferrite is the most conductive element and practically cost. And ferrite has a magnetic permeability between 3,000 to 5,000 range. Okay, so this is again, those are not work done by ourselves, but just to demonstrate the application. So this is by Nissan. So this is a Nissan vehicle, and you can see the receiver coil and the transmitter coil is actually embedded within the concrete material. Okay, so what can we do to make concrete magnetically permeable becomes a interesting research topic, because then you can enhance the power transfer between the two materials. And you can see here, this represents a single receiver coil and multiple on the ground. So when the vehicle is in motion, you can actually see that it continuously charging the batteries in the car. In our laboratory, we have a homemade locomotive, a baby train, if you will. Okay, it's actually a rideable train. So you can see one of our students is driving this train, and we have a, a full track behind so that we can run the trains and doing different developments to the system. And this is our laboratory developed the dynamic wire charging system. So this is the part that I will describe. Okay, our initial charging of the train is actually have a wayside charging station. So these two coils, one is receiver end, and on which is placed on the train, and then there is another coil that is the transmitter coil that is powered by the building electricity. And this is all work done by our undergraduate students, the senior year students. So they developed the entire locomotive, including modifying the power charging using car batteries, and then the power electronics controls. Okay, and the only thing that was not designed by ourselves is the motor of the train or the engine. For the power charging, the wireless power charging, so we have this leads coil that was connected in series, because then they can be used for dynamic charging. And this is the power supply system that converts DC current into AC current, and then that goes through the leads wire for the the magnetic field generation. And this is the receiver end, which has a full bridge system, a half bridge system that would actually convert the magnetic field into electric current. This is what we call the air coil system. So in other words, other than the leads wire, we only use wood plates to form the coil system. Okay, and so as you use the ANSYS modeling of the electromagnetic effects, you can see that you can model the leads coil system. And this black elements within is actually the ferrite metal material, if you will, which has a permeability of about 3,000. And this manufactured ferrites are very, very expensive, but they were able to allow magnetic fields to focus onto the receiver end. So both of these top plates are the receiver, okay, of the electric current. So in this case, we have the ferrite on the transmission side, and this is another design where we put the same ferrites onto the receiver end. As a result, we have the optimal transmission of electric magnetic currents into the system. Electric magnetic field through the system. Okay, but one of the challenge of this design is actually these ferrite materials are very, very expensive, and they are very brittle, so they're not very reliable element. Okay, so in our laboratory, we start to develop our own core elements using concrete. So this is the regular concrete with no steel fibers, and this is the carbon steel concrete with fibers. Okay, concrete without fibers would behave just like wood or air. Okay, actually maybe slightly better because you do have some voids and moisture in it, and but the one with the steel fiber embedded would actually perform very, very well. Okay, and so this is the ferrite coil specimen that we have shown early on, and you can see that with permeability at 3,000, our power transfer efficiency is 9.1%. Okay, this is when we have an input power at 6 volt, and the input electric current at 43.9 watts. Okay, so our output voltage is actually at 22.1 volt, but with only a power current of 4 watts. Okay. Now we can do a lot of things to improve the efficiency by increasing the wattage of the system, but because this system is so small, we limit ourselves to this. So this is the efficiency that we achieve. When we use our steel fiber concrete at 8% of the fiber content by volume, we saw that we actually were able to achieve a 7% efficiency. So it's slightly lower than this 9%, but it's still better than the air coil case. Okay, and this is the air coil case with a larger air space. Okay, so this shows only 6.2% efficiency. So here you see that with air coil, you only have 6.2%, and then with ferrite coil, you actually have 9.1%. And the mixed concrete with fibers, we actually reach 7% of efficiency. So again, it demonstrates that concrete with carbon steel fibers were able to demonstrate higher power transfer than the typical air coil system. Okay, so that is give us a lot of confidence, and this is still ongoing research, and so we are continue to improve. I believe the last set of specimen that we have been able to make was actually at 25% of steel fibers mixed into the concrete material. And so, in summary, we have demonstrated a really a new application of concrete technology that both make concrete itself into a self-sensing element, and also magnetic concrete for wireless power transfer. Okay, we are living in a very different world now, and so the ability to modify building technology to make our world more sustainable is highly encouraged. And but the challenge for us is really to understand something that we don't typically encounter, and that is the electromagnetic properties of concrete. Okay, so now we have to do more research to understand how concrete behave, especially modified concrete for special intent such as self-sensing. Okay, so how can we make concrete more electrically conductive and also magnetically attractive for wireless power transfer? And then there is another component to this that we have not, in our laboratory, that we have not explored is what can we do to make concrete actually electric resistant, so that the idea is to make concrete a EMF shielding element. So in this day and age, we heavily dependent on electric products such as cell phones and such as the wireless communication that we're doing now. Instead of us meeting face to face, we're actually dependent on wireless communication. And so all of those wireless electric devices generate strong EMF fields in our surrounding. So can we make our buildings selectively shielding us from those EMF effects? Should be a very important research topic for the coming century. And so with that, I am concluding my presentation, and I like to entertain any questions from the audience. By the way, if there are technology challenges, I'm glad that the Vidya Institute of Technology is recording this so you can review the presentation. But if we're not able to address your questions, you can always feel free to contact me at my email, schen12@uncc.edu. I think there are time for questions. Okay, so I see a lot of questions being posted. First, to answer Dr. Senthil Kumaran, yes, the whole purpose of the self-sensing concrete is for strength health monitoring. Okay, as I demonstrated in my early on presentation. Okay, and in the voltage versus temperature relation, how the geo-space ratio is affected. I think the geo-space ratio is significant. Again, we have not go into the microstructure evaluation of this. So the percentage of recycled steel residual use in our example, the highest that we have done for self-sensing purpose was 2%. And that was based upon some of the ASTM standard. But now that we have done more, we can increase the steel elements in the concrete material. Okay, so this is from Katam Subsiva Rao. He asked, what about thunder effect on the magnetic concrete? That's a very good question. So as of now, I think the shielding technology exists for isolating magnetic concrete from thunder lightning effects. But I do not think people have actually studied the shock effect from thunderstorm onto the magnetic concrete yet. Okay, very good question. The next question is, apart from ferrite, steel fiber, and air coil, is there any other material that can be used? That is a very good question. So there are some materials that are very highly conductive magnetic field, magnetic effect wise, but so we also try to use a stainless steel, but stainless steel actually has a reverse effect. So stainless steel is very electric conductive, but they are not very magnetically effective. So you have again to explore the material properties of this material. And then there are some ceramics are actually very good magnetic elements. Okay. High tension power lines very near to the magnetic concrete road or structure. So actually the magnetic concrete road for power charging is already embedded with high power lines. So it is part of the integrated component. So these are very high voltage power systems. Okay. Cost impact between self-sensing concrete and general concrete. So because we are using the because we're using the waste steel material, so as of now, the cost is slightly higher than general concrete by a very small fraction, because all the cost that was involved is in cleaning up and sieving out the steel fibers, the waste. Okay. Self-sensing concrete versus smart concrete. So the concept between okay, when I coin smart concrete, I'm really talking about making concrete a functional concrete. Okay. In health monitoring, smart concrete actually means something else. Okay. Any kind of concrete with sensing capability, especially if it has an actuation, meaning it can adjust its resistance to loading, is what we define as smart concrete. So I use a misnomer. What we are describing is not really exactly smart concrete, because we don't have the response component. Okay. Yes, and I will share the PowerPoint with Vidya Jyothi Institute of Technology, so that it can be shared with the participants. I think that is the last. Oh yeah, there is a by Conor Sutia. very interesting question. He asked about self-healing concrete versus I'm not very familiar with self-healing concrete, but that is a very interesting component, because I believe self-healing concrete actually has 2 or 3 types of technology, one of which is self-healing through heating process. Okay, so you have to add energy in order to make the concrete material self-heal. And then there is another type of self-healing concrete. So in other words, I'm not sure if there is a true self-healing concrete technology out there, okay? But the general idea is when you have a crack, the self-healing elements will actually rebond the crack material, okay? Yes, we can use magnetic concrete in rigid pavements.
Sir, can I add a question?
Yes, sir. Yes, ma'am.
What is the most unfavorable high temperature range that can weaken the concrete or even damage the internal structure?
Okay, so in our literature review, as I demonstrate in our laboratory, we are not able to heat the concrete elements to higher than 100 degrees Celsius because of the heating design that we set up. But we know that there are facilities that actually allow the concrete to heat up to 700 degrees Celsius in the fossil power plant scenario. And the grade of concrete, that's a good question. Usually they use high grade concrete for this purpose.
Thank you, sir. And the next question was how to employ image processing to identify pavement distress.
The mixing process?
Image processing.
Okay, so we are using the standard procedures for mixing concrete. Again, it's like a steel fiber concrete, so the mixing process is exactly the same. The only difference is that you have to modify it to have those embedded elements.
Thank you, sir. And what is the percent of recycled steel residuals in concrete?
We have used, as I mentioned, we have used up to 2%. There is a possibility of increasing the steel fiber content, but then at some point you're going to have problem with workability of the mixing of concrete, right? Because the steel fiber tend to absorb water into the system.
Thank you, sir. And apart from ferrite, steel fiber, and air coil, is there any other materials are used?
Yes, as I mentioned, there is possibility of using other magnetic elements, but some ceramics is good. Magnetic had good material magnetic permeability qualities, and I think silver and some copper, some of those elements can be used. Yeah.
Thank you, sir. And how it behaves if high tension power lines are very near to magnetic concrete road or structure?
The whole intent of this study, I mean, of the wire power, is to embed them along with the high power lines. So that question is not an issue, because those are, you have to make sure that they are heavily shielded so that it doesn't cause power leakage and shock people.
Thank you, sir. What kind of application broadly used in smart sensor concrete?
Smart sensor concrete, as I introduced in the beginning of presentation, it's most practical for mass concrete, you know, where you have so much concrete that typical NDT methods will not be able to reach to the interior of the concrete material itself.
Is there is possible for using magnetic asphalt concrete instead of using magnetic cement concrete?
Yes, there are people who are studying magnetic asphalt concrete at this point. Not in my group. Yeah.
Thank you, sir. And how it behaves if high tension power lines are very near to magnetic concrete road or structure?
As I mentioned, our system has high power lines that connect to the magnetic concrete. So one of the approach could be that you can use the transformer to step down on the power effect.
Thank you, sir. And one more question for you. How much max heat generated during this process in human tissues?
How much what?
Heat generated. How much heat generated during this process in human tissues?
Oh, excellent question. Because yes, in the process, one of the effect on the efficiency is the high temperature. We don't have specific numbers, but we do know that the system would heat up. Yeah, good question.
Thank you, sir. And what was the corrosion resistance? What about the corrosion resistance?
Okay, so if the steel fibers are properly treated, usually you will not have any resistance. But because it's what we are using is carbon steel, so it is possible to have erosion. So you have to make the concrete water impermeable. Okay, so I imagine rain can corrode those carbon steel.
Thank you, sir. Why you are using carbon fiber? Any specific reason?
Okay, carbon fiber, again, because it's the lowest cost elements that we can identify. And also in the magnetic application, carbon steel has a higher strength than, higher magnetic permeability than stainless steel.
Thank you, sir. Thank you for answering all our questions patiently. Now I request Dr. Sudarshan, sir, to give the vote of thanks.
Okay.
So, very good evening. It's my pleasure and privilege to proceed the vote of thanks for today's seminar. First, I submit my sincere thanks to our development Vidya provided the opportunity to conduct the international seminar on advancement in concrete technology. I extended my warm thanks to today's chief guest, Dr. Chen Chen, Professor, Civil and Environmental Engineering, University of North Carolina, from US. With his busy schedule, he accepted our invitation. Thank you, sir. Your session is more informative and a nice presentation. We learned lot of things today, like self-sensing concrete, pull-down test, and the concrete electricity transfer, as well as magnetic concrete. It is very useful and very helpful for our researchers and beginners, as well as for those who are working in this area. Thank you, sir. Further, I want to acknowledge the thanks to our Dr. Sai Baba Reddy and the principal Dr. Patpaja ma'am and our beloved HOD Dr. Pallavi Gadri and other faculty and colleagues who involved in this program directly and indirectly in a grand success. I extended my sincere thanks to Mr. Srina and Mrs. Srija and the Monica for their continued support and effort successful conducting for this event in a smooth manner. My sincere thanks to all the participants from various parts of the world for their active participation in the event in a grand success. Thank you, sir.
Thank you. Thank you, everyone.
Participants, I have small announcement over here. Feedback form we have sent in the chat box. Apart from that, I would like to announce that from the next week onwards, 17th to 7th of 3 weeks program, we are organizing as an internship for the students. The students eligible for these are the 3rd year and the 4th year students. Right, so we will circulate it from tomorrow. We'll circulate it. So kindly encourage, if the faculty are there in this group, kindly encourage your students for this internship. And also if the students are there in this participant list, try to attend this. You will be getting the different flavor of the experience from our expert team. So this is the small announcement, and also I would like to thank our resource person today, because I know Sudarshan sir was back to sir because he was very much busy, but still he you could give us time, and you enlightened us with whatever research you have. So surely we will be touch with you, sir. Either our students will be taking guidance from you in one and the other way, and our faculty. So we are very much glad to be. You are the part of this event, sir, and we really enjoyed your session with the whatever new technology you are using. So I really thank you, and also I really wanted to express my gratitude to all participants who are believing and joining for the all the events. So that is really I wanted to mention of that note. So thank you, and we will share the brochure of the internship with you all. Kindly go through and promote it, right? So thank you. So Sudarshan sir, anything you wanted to tell?
Yes, sir.
No, I want to thank everyone being here. Yeah.
Yes, yes. Any participants wanted to share some experience, because 5 minutes we can give time. Participants, because sir is here, we won't get such opportunities all the time. So participants, any participants?
If anyone interested, you can unmute yourself and you can speak now.
Sir, can we use this technology in metro rail, sir?
Sir,
Yeah, participant, whoever wanted to interact with sir, 5 minutes we will give time to you. Kindly introduce and interact with sir.
Hi, sir. Myself, Dheeraj Marshetty. Can we use this technology in the metro rail?
In microwave,
Metro rail, sir. Metro.
metro line. Oh yes, absolutely. Yes, any kind
Okay.
of rail-based is our interest in use this wireless power charging. Yeah.
Anyone interested to ask, interact, or shall we end the session?
Hello, sir. Hello.
Yes.
Yeah, you can carry on. We can hear you.
I am. My name is Unnat Parande from Mumbai, India. Uh, could you please tell us? Could you tell us something about the use of soy methyl ester polystyrene in construction?
Oil. I'm sorry.
Soy methyl ester polystyrene.
I am not familiar with that technology. My apologies. Yeah.
So participants, sir has already provided the mail ID with you. Whenever you are going through or you are having doubts in your research or any further study, you can directly contact sir. Sir will revert back to you, right? So I hope we should end over here instead of extending. Is it okay, sir? Sudarshan sir?
yes, ma'am. Yes, ma'am.
Yeah, kindly go ahead. Thank you very much, sir. Professor Shin.
Thank you. Thank you. Good to talk to everyone.
Goodbye, sir. Goodbye.
Thank you, sir. Thank you, ma'am. And thank you, Sudarshan, sir, for this nice opportunity. Thank you, everyone.
Thank you, sir.